there, thanks for watching Toto Physics. Let's begin our discussion of motion by defining two important quantities, position and displacement. Position is a familiar concept. It's an object's location in space, and for one dimension, we'll use the variable x to denote position. It's impossible to describe something's position without having a frame of reference. So, first, let's establish our reference frame. We can choose the location of this rock as our origin and extend a set of positive and negative axes. The numbers on this axis are arbitrary until we associate a unit with them, so we'll add an m here for meters. Now, we could describe the motion of this rock, but who cares about some dumb old rock? Let's talk about my awesome cat instead. Good boy, Mochi. Now, as our cat friend here begins moving, we can guarantee at least one thing. He can't be in two different places at the same time. That is, as my cat is changing position, the time of day is also changing. Mathematically, this means that Mochi's position can be described as a function of time. And how can we have a function without also considering a graph, right? Being able to interpret the physical, mathematical, and graphical descriptions of a set of motions will come in handy in the future, so we'll consider all three. But first we need something to start moving. So let's say I hypothetically sit Mochi down at x equals 5 meters. We can write this mathematically as x at time equals 0 is equal to 5 meters, or x of 0 is equal to 5 for short. Let's just add this point on our graph. Naturally, being a cat, he doesn't take off immediately. That's just not cool. He lingers for about 3 seconds before going to check out something suspicious close to the rock. Then he moves to x equals negative 2 meters. Feeling unintrigued, he returns 2 seconds later to his initial position at x equals 5 meters. Believe it or not, we can learn something by recording Mochi's various positions. We see that position can be positive or negative. For position, positive and negative don't refer to an abundance or a lack of position, whatever that means. They actually refer to directions, namely to the left or right of the rock. For example, instead of writing negative 2 meters, we could have written 2 meters to the left of the rock. The fact that position includes a direction indicates to us that it is actually a special type of quantity called a vector. Vectors are quantities which contain both a magnitude and direction. Vectors are important and will be discussed in detail in Chapter 3. For now, we'll just recall that position is a vector by including this tiny arrow symbol over our variable. Using position, we can define a new quantity called displacement. Displacement is defined as the change in position of an object. We denote displacement using the Greek letter delta, which means change in, then the variable x from position. So delta x literally means change in position. Another way of writing the change in position is by taking the difference between an object's final and initial positions, which we write as x final minus x initial. A faster way of writing x initial, since it will show up often, is by subscripting it with a 0 and calling it x naught. Likewise, I'll just write the final position as xf. So to compute an object's displacement, we just have to specify the initial and final states that we're interested in, which we usually distinguish by a given start and end time. Let's compute Mochi's displacement after 3 seconds. We start by copying our definition here. The displacement after 3 seconds is equal to Mochi's final position minus his initial position. Here, his final position will be his position at time equal 3 seconds, while his initial position is that at t equals 0 seconds. Now we just fill in numbers. This becomes negative 2 minus 5, or negative 7 meters. This means that in the first 3 seconds, Mochi moved 7 meters from his starting position in the negative direction, or in other words, to the left. Notice that the displacement, like position, has a magnitude and direction, which means that this quantity is a vector. So we should probably add our arrow symbols. We could have also computed displacement graphically by just considering position at time equals 3 and time equals 0 and subtracting these 2 points. we would have also seen that the displacement after 3 seconds was -7 meters. Now here's a warning before we proceed. Displacement is not the same as distance. Distance is the total length traveled within some time. Displacement is the change in position. And recall that this is a vector quantity, so it tells us something about direction as well. Distance, on the other hand, is what we call a scalar quantity, meaning it contains no information about direction. The distinction is made more clear with an example. Let's compute the total distance Mochi traveled during this little adventure. Well, first he went from his starting position at 5 meters to 2 meters left of the rock. That's a total of 7 meters. And then he went back. That's 7 more meters. This makes the total distance traveled by Mochi 14 meters. Conversely, let's consider Mochi's total displacement. Let's start with our definition. The total displacement is equal to the final position minus the initial position. That is, Mochi's position after 5 seconds minus his initial position at 0 seconds. Then we substitute in numbers, 5 minus 5, which gives us a whopping total of 0 meters. There you have it, folks. Mochi's total displacement was 0 meters. Nada. Zilch. Nuttin'.
What?
But don't despair, we actually learn a lot from this nothing here. Had we just been told that Mochi went a distance of 14 meters, there would be no telling where he ended up. But a displacement of 0 is in fact quite descriptive because it tells us that after 5 seconds, I'll find Mochi back exactly where he started, 5 meters to the right of the rock.